Hello everyone and welcome to this explainer. Today we're taking a wild journey that bridges two absolute extremes of our natural world. We're going from the completely invisible, microscopic realm all the way to the massive, sprawling expanse of the world's most daunting deserts. We're looking at a pretty groundbreaking piece of research that asks a huge question. Can we use the smallest organisms on Earth to solve one of its absolute biggest environmental crises? Okay, let's dive right into this.
Think about it for a second. How do you stop a moving desert? It sounds a bit like a philosophical riddle, right? But honestly, this is a very real, very urgent logistical nightmare. You see, the core problem with desertification isn't just the lack of water. It's the fact that the ground itself is literally constantly shifting. The wind just relentlessly moves the surface of the sand. And because of this, it's virtually impossible for fragile ecosystems to recover on their own. You can't just, plant a shrub and hope for the best, because those shifting sands will either bury it completely or expose its roots before they ever even have a chance to take hold. The land is essentially a massive moving target.
And that moving target? It's only getting bigger. When we look at the primary drivers of desertification, we're really seeing a perfect storm of environmental pressures. We're dealing with prolonged drought, the massive overarching impacts of climate change, widespread deforestation, and agricultural overgrazing. All these factors are combining to drive global land degradation on a mind-boggling scale. They're basically slowly turning productive, life-sustaining land into totally barren desert. The sheer scale of this problem is so immense that our traditional methods, like planting trees or trying to build physical barriers, are just way too slow or wildly resource-intensive. We desperately need a rapid, large-scale solution. We literally need a way to freeze the sand in place.
Enter the real hero of our explainer, the biological soil crust. Now, this isn't concrete, and it's not some synthetic mesh. It's a very thin, completely natural layer made entirely of living microorganisms. We're talking things like cyanobacteria, fungi, and mosses. And working together, they act as a living protective covering for the sandy ground. I just want you to pause and think about the unbelievable contrast in scale here. We are talking about utilizing tiny, single-celled microbes to build biological armor that is actually capable of taming massive rolling sand dunes. It's basically nature's own built-in stabilization mechanism.
Now, what's truly fascinating about this breakthrough is the timeline. Under normal, wild conditions, these biological crusts take many, many decades to develop on their own. It is a painstakingly slow ecological process. But researchers at the Chinese Academy of Sciences have engineered a total breakthrough. In experimental areas near the harsh Taklamakan Desert over in northwestern China, they've actually managed to fast-track this natural development. So instead of waiting decades, they are forming strong, stable crust in just 10 to 16 months. They've essentially grabbed the remote and put nature on fast forward.
So how exactly are they pulling this off? Well, let's walk through the mechanics of the process because it is brilliantly elegant in its simplicity. Step 1. The researchers cultivate specific cyanobacteria in a controlled laboratory setting, growing massive amounts of this solid inoculum. Step 2. They take this living solution out of the lab and literally spray the microbes directly onto the loose, shifting desert sand. Step 3. Once they're applied, the microbes start to multiply, they spread out, and they release a natural adhesive. And finally, Step 4. A stable surface layer successfully forms. They are quite literally seething the sands with life. And this beautifully illustrates exactly why this process actually works. As these microscopic organisms grow on the sand, they, quote, release sticky substances that act like a natural adhesive. They essentially weave this microscopic sticky net that binds the loose sand particles together. And you'd be surprised, this living layer is incredibly tough. It creates a unified surface that can actually withstand extreme wind erosion. Plus, by keeping all that sand locked down to the ground, it significantly dampens the impact of those destructive dust storms that constantly plague these arid regions. But hey, the magic of this biological crust doesn't stop at just holding the sand in place. It actually gives the developing soil a whole set of cascading superpowers. The crust helps retain critical moisture and heavily limits water loss through evaporation, which, as you can imagine, is absolutely vital in a desert. It keeps essential nutrients trapped right close to the surface where they're needed. It slowly builds up organic material over time, and incredibly, some of these cyanobacteria can literally absorb nitrogen directly from the air, naturally fertilizing the ground. All of these factors combined completely change the game. By naturally enriching the soil and keeping it stationary, grasses and shrubs finally have a fighting chance to actually take root and grow.
So the crucial point really comes down to this absolutely staggering figure, greater than 90%. In laboratory conditions, testing showed that areas treated with this microbial spray experienced a staggering reduction in wind-driven soil loss of over 90%. More than 90% of the sand that would normally just be blown away, contributing to further desertification and massive dust storms, was successfully held tightly in place by this thin, living crust. It's a monumental finding. It proves that the biological mechanics at play here are incredibly effective.
Okay, but as focused learners, we always need to ground our enthusiasm in the facts, right? So, time for a quick reality check. If you've been reading about this online, you might have seen some highly dramatic, heavily edited split images showing a barren desert instantly turning into this lush green paradise. Well, the source material explicitly points out that those viral images are dramatic composite illustrations. They are absolutely not literal trial results. The real scientific results are incredibly profound, yes, but visually they are much, much more subtle. You're generally looking at a thin, often dark crust forming on the sand, not an instant tropical rainforest. True ecological restoration is a nuanced, gradual process.
It is also super vital to understand that this biological crust is not some invincible silver bullet. At the end of the day, it is a living, fragile system, and it faces major threats from really simple disturbances. Just human walking, off-road vehicles, and animal grazing can easily break the crust, which instantly undoes months of microbial growth and exposes the loose sand underneath all over again. Furthermore, its long-term effectiveness relies heavily on unpredictable weather patterns, so actually deploying this solution requires incredibly careful land management and really strict protection of the treated areas just to make sure the crust remains totally undisturbed.
Now, let's zoom out a bit and see how this builds at the macro level. Proving something works in a lab or a small trial area is one thing, for sure, but actually reversing desertification requires deployment on a massive scale. Currently, this solid inoculum of cyanobacteria has been officially incorporated into China's new 3 North Shelter Bell program. This represents a huge, immediate transition from tiny microengineering to massive landscape-level deployment.
Just try to wrap your head around the sheer scale of this rollout. Over the next 5 years, the program expects to rehabilitate between 80,000 and 100,000 mus of desert. To put that into perspective, that translates to roughly 5,300 to over 6,600 hectares of land. We are talking about taking something cultivated in tiny petri dishes and spraying it across thousands of hectares of incredibly hostile desert terrain. It is an unbelievably ambitious scale-up of a nature-based solution. And it's interesting to note that the researchers and institutions behind this breakthrough view it as far more than just a localized project. The source material actually frames this innovative achievement as having made a major breakthrough in desertification control, stating that it provides, quote, a Chinese solution for global desertification management. It's very clear that the ambition here is to offer this microbial methodology as a nature-based template, one that could potentially be adapted and deployed to combat land degradation in arid regions all over the entire globe. Which brings us to a really compelling final thought to leave you with today. Is microengineering the ultimate key to our macroclimate survival? As we face massive planetary scale challenges like rapidly expanding deserts, perhaps the most effective tools we have aren't giant machines or massive concrete walls, but rather the invisible living ecosystems right beneath our feet. By understanding and accelerating the work of a simple single-celled cyanobacteria, we might just learn how to literally hold our shifting world together. Thank you so much for joining me for this explainer, and remember to keep questioning the world around you.